This video is going to focus on neutralization reactions and the pH of salts. A neutralization reaction is any time you have an acid and a base reacting. All right, acid and base reactions are called neutralization reactions. Essentially, the acid will donate a proton to the base. Typically here, you're going to get a salt and water as your products, or maybe you just get a salt if you don't have maybe an OH here from the base. So we'll look at that as we go through. So there's four types of neutralization reactions. And basically, you've seen these reactions before. Maybe we looked at them as double replacement reactions or whatever. So this isn't really a big deal here. But the first type is going to be when we have a strong acid reacting with a strong base. The products are always going to be a salt and water. So if you notice here in this first example, we have HCl, which is a strong acid, and NaOH, which is a strong base. Essentially, they're both compounds. This is going to be a double replacement reaction. All right, the Na is going to be with the Cl in the product side here, and the H is going to be with the OH, and it's going to form water. So your products here are a salt and water. All right, so this is not any new reaction. This is just basically a double replacement reaction, but this is a neutralization reaction because we have an acid and a base reacting here. So that's called a neutralization reaction. Let's look at another example here. We have HClO4 plus NaOH. So we have a strong acid here for perchloric acid. Again, we have sodium hydroxide. That is a strong base. So when we do this, it's going to be another double replacement reaction. The Na is going to switch spots essentially with the H. So you're going to have NaClO4 plus, again, it's going to be H2O here. All right, HOH, which is H2O. We get a salt plus water. All right, so that's the first type of neutralization reaction. Anytime you have a strong acid reacting with a strong base, you're going to get a salt plus water, but basically it's a double replacement reaction. But anytime we have these acids reacting with bases, those are neutralization reactions. The second type here is when we have a strong acid reacting with a weak base. The salt is going to form, but you might not get any water present if there's no OH present in the base. Remember, a lot of weak bases don't have OH present in them. Think of something like NH3. There's no OH, so it can't form water if there's no OH there. So let's just look at a quick example here. If we have HCl, that's a strong acid reacting with NH3. So what's going to happen here is you have to recognize that this is your acid. It's going to donate NH plus to the NH3, forming NH4 plus, but then you're going to have Cl minus. So what does it do? They combine. All right, NH4 plus, Cl minus combine to give you a salt, NH4Cl here. All right, essentially you could write it as NH4 plus Cl minus. All right, but they typically going to come together here to form the salt. We don't get water because there was no OH present in the weak base. But again, this is a neutralization reaction. You have an acid reacting with a base here, but in this case, we don't get the water forming. Third type is when we have a weak acid reacting with a strong base. We still have an acid reacting with a base, so this is a neutralization reaction. We're going to get a salt plus water here, and the salt is going to be the conjugate base of the weak acid here. So if you look at this, we have the weak acid, acetic acid, reacting with NaOH, which is a strong base. Essentially, you're going to look at this again as a double replacement reaction. So when the sodium and the hydrogen switch spots, you get sodium acetate here. Essentially, the C2H3O2 minus here is going to be our conjugate base of the weak acid. And then you have water forming again. So typically here we see a salt plus water forming. And this is another example of a neutralization reaction because we have an acid reacting with a base. But again, you've seen this before as a double replacement reaction. The fourth type here is when you're going to have a weak acid and a weak base reacting. The products are going to be the conjugate base and the conjugate acid or salts of them. So if you notice in this example, we have acetic acid here reacting with NH3. We can't get water forming because we don't have the OH present in the weak base, but we know that the weak acid is going to give up an H plus to the NH3. So you're going to form NH4 plus plus a C2H3O2 minus. They could come together here and form a salt, being NH4 C2H3O2. That is a possibility. They could be separate here as well. But notice we're not going to get the water part. You'll get the salt, but you won't get the water here because we don't have the OH present with the weak base. All right, so this is another example of a neutralization reaction when you have an acid reacting with a base. Let's try a few here. Let's write the products here for these acid-base reactions. What I would do is I would pause the video right now, see if you can do these on your own. Again, you pretty much know how to write reactions already, but these are neutralization reactions because you have an acid reacting with a base. So I would pause the video, try them, and when you rejoin, we'll see how you did. So pause the video right now. Hopefully, these are the answers you got here. Just be careful. I didn't necessarily go through and balance them. Notice for the first three, you do get a salt plus water forming because the base all have OH in them. But when you get to the last one here, the NH3 doesn't have OH in it, so you're not going to get a water forming. You're just going to get the salt forming. But typically here, these are reactions you already know how to do. But realize here, more specifically, these are neutralization reactions because we're reacting an acid with a base. We are looking at these neutralization reactions because we need to think about the acid-base properties here of the salts that formed. We already know that when you do a neutralization reaction, typically you're going to see a salt plus water forming. Sometimes you just get a salt forming. And these salts that are produced in these neutralization reactions are not always neutral. So the salts that are produced might actually contribute here to the overall pH. We already know that ionic salts here are typically going to dissociate 100% into their ions. That's what happens when you put an ionic solid in water. And sometimes here, these salts can hydrolyze. What that means is they can react with water to actually produce acidic or basic solutions. So now we need to actually look at the salts that form and think about whether or not they will actually contribute to the pH here, whether or not they will hydrolyze with water to produce an acid or a base solution here. So some general statements we need to think about first. Anytime you have the salt that was formed from a strong acid and a strong base, like NaCl, all right, they're not going to hydrolyze and the solution is going to be neutral or a pH of 7. So essentially, if you have a salt here, you have to be able to reverse engineer, if you will, where it came from. So if you have NaCl, all right, you got to think about this logically. NaCl here obviously had to come from Na something and Cl something. Well, if Cl is minus, well then that means it's going to be with the H plus. If Na is plus, that means it's going to be with the OH minus. So essentially, NaCl had to come from the reaction of NaOH plus HCl. If you don't believe me, write the reaction, and you'll see you get NaCl plus water here. So you see how I took the salt itself and I reverse engineered which acid and base it came from by splitting it apart into its ions and putting the negative ion of the salt with H plus, the positive ion of the salt with the OH minus. So if you look at this now, this is where the thinking comes in. You can see that NaOH is a strong base, HCl is a strong acid. So NaCl came from a strong base and a strong acid. Therefore, it's going to have a neutral pH or a pH of 7. It's not going to react with water to add anything here to the pH. So NaCl will not react with water. Something like Ki as well will not react with water. Let's see where Ki came from. So if we split Ki here into its ions, you'd have K plus and I minus. You put the H plus with the minus ion, so it came from Hi, and then the K plus had to come from KOH. All right, the K plus will join up with the OH minus, and the I minus will join up with your H plus. So if we look at this here now, KOH is a strong base, that's one of the strong bases. HI is a strong acid. So Ki came from a strong base and a strong acid. So it's not going to hydrolyze with water here. It's not going to react with water. It's going to have a pH of 7. It's going to be neutral here. That's basically what you need to do with all of these salts. You need to reverse engineer where they came from and then analyze the acid and the base that it came from and see if they're strong and if they're weak, and then you'll be able to figure out what the salt is going to do here. So any salt that comes from a strong acid and a strong base is not going to hydrolyze with water, and it's going to be neutral. Salts that came from a weak acid and a strong base will hydrolyze here, and the overall solution will be basic, or a pH greater than 7. All right, so this kind of makes sense. If it came from a weak acid and a strong base, you kind of like in your head can see like, oh, well, the base is stronger, so it's winning. You're going to have a basic pH here when this hydrolyzes. Essentially, the anion part of the salt is going to act as a base here. And we'll look at what that looks like here in a second. But again, let's do this little practice here. We have this sodium acetate, NaC2H3O2. Again, this is a salt, so you have to see where it came from. So you break it apart into its ions. You have Na plus, and then you have this C2H3O2 minus. You put the minus with H plus, so then that's going to be HC2H3O2. You put the plus ion with OH minus. All right, so then that's going to make this NaOH. So now you analyze both of these. NaOH is a strong base. HC2H3O2 is a weak acid. So sodium acetate came from a weak acid and a strong base. So it's going to hydrolyze or react with water to form a basic solution here. All right, remember, salts will fully dissociate into their ions, and one of those ions might be able to hydrolyze with water here to give us a contribution to our pH. And in this case, that's what happens. One of the ions here is going to hydrolyze with water and give us a basic pH because this salt came from a weak acid and a strong base. Once you know that a salt is going to form a basic solution here, in your head, you know a part of the salt, either the cation or the anion here, is going to react with water to give us OH minus. We know we have to form OH minus because we're going to form a basic pH here, a basic solution. So here's a little trick. If you need to form an OH minus, you want to take the minus part of the salt, the anion part of the salt, react that with water, and then that will generate your OH minus. So you can see here, we already said for this sodium acetate, it's going to give us a basic solution when the salt hydrolyzes with water. So if we want to form OH minus, we need to take the negative part. If we want to form OH minus, we want the minus part of the salt reacting with water. So we took the C2H3O2 minus part of the salt. That's going to react with water here, and it's going to be in equilibrium. It's going to form here OH minus plus the weak acid here, acetic acid. Essentially, you just did the reaction. The water gave up the hydrogen, forming OH minus plus the weak acid here. Notice these hydrolysis reactions are going to be equilibrium reactions. They're going to have the equilibrium arrows. That's very important. So again, just to recap, once you know a salt came from a weak acid and a strong base, you know it's going to form a basic solution. You need to form OH minus, so the minus part of the salt is going to react with water in equilibrium to form OH minus here. That's the base that needs to form in order for this salt to be basic when it hydrolyzes with water. The Na plus part is not going to do anything here. Think about that. If that reacted with the water, at most it would pick up an OH minus, leaving an H plus on the product side. Well, that doesn't make sense because we already said we need to form a base here. We need to form an OH minus. This requires a little bit of thinking, but once you kind of think it through, it makes complete sense. Anytime you have a salt of a strong acid and a weak base, it's going to hydrolyze and form an acidic solution. So it's kind of the opposite here of what we just saw. It makes sense. If a salt is coming from a strong acid and a weak base, it makes sense that the acid is stronger, so it's kind of winning here. So you're going to form an acidic pH. All right, but you can do this by analyzing the salt here and figuring out where it came from. So if we have NH4Cl as our salt, remember this is a salt here, break it apart into its ions, you're going to have NH4 plus Cl minus. All right, so when you have the Cl minus, you know the H plus needs to go with the minus, so that means it came from HCl. And then when you have your NH4 plus, it's going to join up with the OH minus. The plus is going to join up with the OH minus always. So that means this salt came from NH4OH and HCl. HCl is a strong acid, NH4OH is a weak base. So I immediately know here that the acid is winning. I'm going to form an acidic pH. Part of this salt is going to hydrolyze with water to give me an acid. Once I know I need to form an acid, in my head I should be saying, okay, I need to generate H plus. So if I need to form H plus here, because this is an acid, I need to take the plus part of the salt, hydrolyze it with water, react it with water to form H plus. So if you notice here, in this particular example, all right, we took the plus part of the salt, the NH4 plus, we reacted it with water. It's going to be in equilibrium here, and we're going to form H plus. H3O plus essentially is H plus. So the NH4 plus is going to give up a hydrogen to the water, forming your acid plus NH3 here. Okay, we already said that this is going to form an acidic pH, so we need to generate H plus. So you take the plus part of the salt, react it with water, put it in equilibrium, and that's how you get your acid forming here. Again, this does require a little bit of thought, but if you can kind of think your way through this, you'll see it makes complete sense. The last thing we want to look at here is, what if you have a salt that came from a weak acid and a weak base? Well, these do hydrolyze, but it depends on the Ka and the Kb values for both. Okay, so you kind of have to compare Ka and Kb values here. So again, if we look at this particular salt, in this case here, NH4C2H3O2, obviously if you split it apart into its ions, you have NH4 plus and you have C2H3O2 minus. So the minus part is going to go with the H plus, so you have HC2H3O2. NH4 is plus, so it's going to join up with the OH minus essentially. So the reaction that took place to generate this salt, all right, came from a weak base and a weak acid. All right, so these parts will hydrolyze, but I need to analyze Ka and Kb values here for both. If the Ka is greater than the Kb, then I will generate an acidic pH here. If the Kb is greater than the Ka, then we're going to generate a basic pH. And if the Ka and the Kb are equal, then it's just going to be a neutral pH here. So anytime you have a salt that came from a weak and a weak, you need to look at the Ka and Kb values here to see what pH is going to form. So it does require a little bit of thought here and a little bit of analysis, but otherwise it's not too bad. If we continue with this example here, so if we take the NH4 plus from our salt, hydrolyze it with water, remember it was plus, so I'm going to form H plus, or in this case H3O plus. That has a Ka value of 5.6 times 10 to the minus 10th. Well, if I look at the minus part of the salt here, the C2H3O2 minus, that's going to hydrolyze to form OH minus. So it's going to react here with the water in equilibrium, forming OH minus. Because I formed OH minus, it's going to have a Kb value here because this is a base. Well, notice when you compare the Ka to Kb values for both, they're exactly the same. So this salt, even though it came from a weak acid and a weak base, is just going to be neutral because the Ka and the Kb, when you compare them, are exactly the same. All right, so these are the things you need to think about when you're looking at one of these salts. Where did it come from? And then you use that to figure out whether it's going to be a neutral pH, acidic pH, or a basic pH. Understanding these acid-base properties of salt is very important. We will use this idea in titration problems, so we need to be able to do this here. For each of these, we want to predict whether an aqueous solution of the following salts will be acidic, basic, or neutral, and we have to prove this now with appropriate equations. So I'll do the first one with you, and then I'll let you try the rest on your own and see how we do. So the first salt we have here is NH4NO3. So the first thing I need to do is figure out where this came from. All right, so I know I'm going to split it apart into its ions. I'll have NH4 plus and NO3 minus here. The minus is always going to join up with the H plus. The plus is always going to join up with the OH minus. So when I look at these two substances, all right, NH4OH is a weak base. HNO3 is a strong acid. So this is another reason why you need to know your strong acids and strong bases here. So this salt came from a weak base and a strong acid. So the acid is stronger. So I know this is going to form an acidic pH here. All right. Part of the salt is going to hydrolyze with water to give me H plus. All right. So if I want to form H plus, I need the plus part of the salt to hydrolyze with water here. So in this salt, that's the NH4 plus. So the NH4 plus is going to hydrolyze or react with water. It's going to be in equilibrium with its ions. It's going to give up. Remember, you're trying to form an H plus here. So the NH4 plus is going to give up an H plus to the water, forming H3O plus. That's the H plus that I needed to form. We said this needs to be acidic. Plus then, the NH4 plus lost the H plus, so it's going to be plus NH3 here. All right, so that would be the reaction that would take place. We needed to form an acid because this came from a weak base, strong acid. So the plus part of the salt hydrolyzes with water in equilibrium to form your H plus. So now I want you to try the next three here. All right, determine where the salts came from, determine whether they're going to be acid, base, or neutral, and then prove this with appropriate equations. And when you rejoin, I'll have the answer here for you. So pause right now and try this. Hopefully, these are the answers you got here. The second one is going to hydrolyze to form a basic solution because it came from a strong base, weak acid. So if we need to form a base, that's OH minus. So the minus part of the salt is going to hydrolyze with water here to generate the OH minus. The last two both came from a strong base, strong acid. So they're both going to be neutral. And they're not going to have any reaction here with water. So you definitely need to be able to look at a salt, figure out where it came from, determine whether it's going to have an acidic, basic, or neutral pH, and then determine any reactions that might happen here with water. This is definitely a skill you need to have. Whenever we're doing problems here that involve finding the pH of a salt solution, first thing you need to recognize is, okay, this is a salt. You have to basically figure out whether or not the salt is going to hydrolyze to form an acid, a base, or a neutral pH. And this is basically what we just did on the previous slides. So you will have to write the appropriate equilibrium reaction here for the hydrolysis and realize that if H plus is formed, you will need a Ka. And if you are forming OH minus here in your hydrolysis reaction, you will need a Kb. Very oftentimes in these salt problems, you will need to use that Ka times Kb equals Kw equation in order to get the equilibrium constant that you need. So these are pretty much going to be equilibrium problems that you're used to. You just have to pay attention to whether or not that salt is going to be acidic, basic, or neutral here. Let's look at this first example. It says calculate the pH of a 0.10 molar NH4Cl solution. The first thing I recognize here is that this is a salt, all right? It's not, an acid or base. This is a salt. You have an NH4 plus Cl minus. It's going to be a salt here. Not to mention, they're giving me a Kb value for NH3. So immediately that kind of alerts me to the fact here that this is a salt because I don't see NH3 explicitly written here in that substance. So this is another thing that kind of keys you in that this is a salt here. So now you have to analyze this salt. So NH4Cl, all right, where did that salt come from? Well, remember, if you break it apart into its ions, we have NH4 plus, which would have to combine with the OH minus, and then the Cl minus part of the salt would have to combine with the H plus. So this salt came from a weak base, strong acid. So the acid is winning. I need to generate an acid here. All right, if I need to form H plus, I need to take the plus part of the salt, react that with water to form the H plus. So the reaction we're going to be doing here is the NH4 plus reacting with water here in equilibrium to generate the acid, the H3O plus, plus obviously NH3 here. So I know that this salt needed to be acidic, so I need to generate the H plus, which is what I'm doing. The plus part of the salt is hydrolyzing with water to generate that acid, all right? Because we are forming an H plus, I need a Ka value. Right now, we have a Kb value, so you'd have to find this. We know that Ka times Kb equals Kw. Kw is 1 times 10 to the minus 14th. So essentially, what we're going to do here is you're going to solve for Ka. So you're going to have 1 times 10 to the minus 14th divided by your Kb, which was 1.8 times 10 to the minus 5th, and you get the value of Ka here. Again, this requires a little bit of thinking. Because you're forming the acid, the H plus, you know you need a Ka value. But now you're ready to do an ice table here and go about solving your problem for this equilibrium reaction. So we already know the equilibrium reaction that we're doing here. We're going to take the plus part of the salt, hydrolyze it here, react it with water, equilibrium, forming the H plus, which we said that needs to form because this salt is going to be acidic, plus the NH3. So we set up our ice table. Water does not participate in the ice table because it is a liquid. We plug in our initial values here. We know that the NH4 plus, all right, is going to be 0.1 molar here. Notice that the NH4Cl is what you're given the concentration of. Well, remember, this is going to completely ionize here. It is an ionic compound. It dissociates 100%. So if you know the concentration of the original compound, it's a 1-to-1 ratio. You know that that is the exact concentration here of the NH4 plus. Both products are going to have an initial concentration of 0. So we have to think about the change here in terms of X. Obviously, the reactant's going to lose X. This is all 1-to-1. The products are going to form, so they're both plus X. We fill in our values here now for equilibrium. Again, this is going to be an X approximation problem. So I crossed it out there in the table, but realize I'm just doing that to show you that you would do this when you were doing the problem and doing the math here. So you'd have to set up your Ka expression because you're forming H3O plus here, which is an acid. So when you write your Ka expression, plug in, solve for X, that's going to be equal to the concentration of H plus, which is 7.5 times 10 to the minus 6 molar here. All right, now that you have the concentration of H plus, you know how to find the pH. You need to do the negative log of that concentration, and you get 5.12. So this is the basic gist of how you would go about doing a pH problem involving a salt. It just requires you to analyze that salt, figure out whether it's going to produce an acidic, basic, or neutral pH, and then figure out the equilibrium reaction that's going to take place. And then you do a normal ice table here, plug in, and solve for your pH. We have one last example here that we can do. We want to calculate the pH of a 0.30 molar NaF solution. They're giving me the Ka value for HF. So immediately I know, okay, something's going on here because I'm given the Ka for HF, but they're giving me the concentration of NaF. Well, hopefully you realize here that this NaF is a salt. It's Na plus F minus, it's an ionic salt. So now I have to analyze where this salt came from in order to figure out if it's going to give me an acidic, basic, or neutral pH. So if I break the salt apart into its ions here, obviously it had Na plus and F minus. So the minus part always combines with your H plus. So it's going to be HF is the acid it came from. And the Na plus here is going to combine with the OH minus. So the base it came from was NaOH. So when I analyze these, NaOH, I need to know, is a strong base, all right? HF is a weak acid. Be careful here. It's not one of the strong ones. So this salt came from a strong base, weak acid. The base wins. I'm going to form a basic pH here. So in my head, I know if I'm doing base, I need to form OH minus. When part of this salt hydrolyzes with water, I need to form OH minus. So if I need to form OH minus, I'm going to take the minus part of the salt and react that with water. So the minus part of the salt is the F minus. So I'm going to have F minus reacting with water here. It's going to be in equilibrium. These hydrolysis reactions, these reactions with water are going to be in equilibrium. The F minus is going to pick up the hydrogen from the water to form HF plus OH minus here. Remember, you need to form an OH minus here because you need to form a base. If you didn't get your OH minus here, you know you did something wrong, right? So that keys you in a little bit on what the products are going to be as well here, right? Because you're forming OH minus, just an FYI, you will need a KB. So right now we have a Ka, but we'll worry about that in a little bit. We can do our ice table here. The initial concentration of our F minus, well, remember here, NaF is an ionic solid. It's going to dissociate 100%. If you know the concentration of the NaF, it's a 1-to-1 ratio. You know the concentration of the F minus itself. It's going to be 0.30 molar. Water is a liquid. It's not going to participate in the equilibrium. Both of your products initially are going to be 0. So our reactant's going to be losing some value of X. Both products are gaining some value of X here. And when you set up your equilibrium values, you have 0.30 minus X molar, and both of your products are going to be X molar here. Again, we have an OH minus forming, so I need to write a KB. Before I do that, I need the actual KB. So I'm going to need to use Ka times Kb here equal to Kw, which is 1.0 times 10 to the minus 14. When I solve this, all right, essentially what I'm going to have is Kb equal to 1 times 10 to the minus 14 divided by the Ka, which they told me was 7.2 times 10 to the minus 4th. So my Kb for this problem is going to be 1.4 times 10 to the minus 11th here. All right, because I formed OH minus, a base, I need a Kb. Be very careful with that with these salt problems. Now I need to write my Kb. So Kb would be equal to products over reactants. So we're going to have the concentration of HF times the concentration of OH minus all over the concentration of F minus here. I can plug in what I know. The Kb we just found, 1.4 times 10 to the minus 11 equal to X squared all over 0.30 minus X. We can do the X approximation here because this is a weak problem. Makes solving for X a little bit easier. When I do solve for X here, I get X equal to 2.0 times 10 to the minus 6th molar. And remember here, X was equal to OH minus. Pay attention to your ice table. This is the concentration of OH minus here. All right, so when I do the negative log of this, that's going to be a POH. So POH is going to be equal to the negative log of the concentration of OH minus. That's going to be the negative log here of 2.0 times 10 to the minus 6. So my POH, when I do the math here, is going to be 5.70. Again, if you got this answer, you know it's not right because this couldn't be your pH. If this is a base, you have an acidic pH essentially. So that's how you know, oh, this is your POH. So we know pH plus POH equals 14. 14 minus the 5.70 gets us our pH, which is 8.30. And this answer makes more sense because it's in the base region, and we know this salt is going to hydrolyze to give us a base. So that's the basic gist here of how you would do one of these pH problems with a salt. You really do need to think a little bit more. And again, this is a very important section because we use these ideas here of these salts hydrolyzing with water in titration problems. So make sure you're really good with this section.